All right, 6.6 is the derivative and integral practice for transcendental functions. And you might be asking yourself, what are transcendental functions? Those are basically like your logarithm, your exponent, and your trig functions. Let's see, I pulled up a definition here for you from Wolfram Math World. So a transcendental function is a function which is not an algebraic function. In other words, a function which transcends, i.e. cannot be expressed in terms of algebra. So examples that they included here are exponential, trig functions, and then the inverse of both of those types of functions, which would include your logs. Okay, so we're just going to introduce you to a couple new derivative and integrals. And let's start with the integrals. So I'm going to do one example. Actually, I'm going to do two examples where I derive the things that I gave you right here. So integrals of the 6 trig functions. Now you already know the integral of sine and the integral of cosine. The new ones here will be these 4. And I'm going to go ahead and I'll derive the cotangent integral. And I'll also derive the cosecant integral. And your textbook has done tangent and secant for you. So let me put this back. The integral of cotangent is basically going to be the ln of the absolute value of sine, or the negative ln of the absolute value of cosecant. Okay, and so when I do, I'm going to get this one here. So I can say if I want the integral of the cotangent of x dx, I can rewrite this so that I can rewrite it as the integral of the cosine of x over sine of x dx. All right, well, and I can actually rewrite that so I have a reciprocal function. So I can rewrite it as 1 over sine x times cosine x. Well, now this one becomes really easy to integrate. So this is a reciprocal function, and the integral of the reciprocal function is the ln, absolute value of whatever the input is here, or the denominator, I should say. So this is going to end up being the ln of sine x plus c. And just to double check that, if I took the derivative of this, okay, so just to make sure I get back to where I started, if I take the derivative with respect to x of ln of sine x plus c, well, the derivative of this would be 1 over sine x, and then I have to chain rule that, and I'd get cosine x, right? And the derivative constant would become 0. So this would become, in fact, cosine x over sine x, which is, in fact, cotan x. Okay, so that's just double checking my work, okay? But basically, you can either derive it each time or you can memorize it. Okay, another one I want to do, and this one gets quite complicated, but I'm going to show you how to come up with the integral for cosecant, cosecant x, not just cosecant. We need to have an input, cosecant x dx. Okay, so this one gets a little bit tricky because the question is, what would we take the derivative of to get cosecant? Well, in all actuality, there's nothing that we take the derivative of to get cosecant. So what's the function that I'm going to get back to? Okay, so we have to kind of do a little bit of, what would your book call it? We have to be clever. Okay, so let's just think to ourselves, let's recall a couple of derivatives that we do know. So if I take the derivative with respect to x of cosecant x, I get cosecant x cotangent x. And if I take the derivative with respect to x of cotangent x, well, that just leaves me with cosecant squared x. Okay, so I'm going to do some crazy stuff here. So what I'm going to do is I'm going to take what I originally had, and I'm going to make it so that I have a cosecant cotangent and a cosecant squared in there. Because if I can get that, then I can say, well, originally then what I would have taken the derivative of would have been something that would have had cosecant x or cotangent x in it. Okay? So here's what we're going to do. I'm going to bring this down here. Okay, so instead I'm going to rewrite it by basically, oops, let's put the dx last. I'm going to multiply it by a fraction that involves cosecant x and cotangent x. So what I'm going to do is I'm going to multiply it by this fraction, cosecant x plus cotangent x. And I'm allowed to do that as long as I make it like as if I'm multiplying by 1. So I do the same thing on top and bottom. Okay, so now I'm going to go ahead and distribute. So I'll end up with cosecant squared x plus cosecant x cotangent x, right? I'm just distributing all over cosecant x plus cotangent x. Okay, now I can rewrite this as a reciprocal function so that I have 1 over my denominator times the stuff up top. And that's what I'm going to do now. I'm going to rewrite it as 1 over cosecant x plus cotangent x times my numerator, which was cosecant squared x plus cosecant x cotangent x. Okay, so what I'm going to do now is I am going to, this reciprocal function, I can go ahead and integrate. Okay, so that's going to basically give me ln of cosecant x plus cotangent x plus c. Okay, now think about this. If you were to take the derivative of this, you'd get 1 over this stuff times the derivative of this stuff, right? So you'd end up with, the derivative of cosecant x is cosecant x cotangent x, and the derivative of cotangent x is cosecant squared x. So you'd end up with all this. So let's go ahead and let's do that. So I'm now going to take the derivative and see what I get here. So of ln of cosecant x plus cotangent x plus c. So doing that, I get 1 over cosecant x plus cotangent x times the derivative of the inside. So the derivative of cosecant x is cosecant x. Sorry, it's negative, right? Derivative of anything with a c is always going to be negative. Cosecant x cotangent x plus the derivative of cotangent x, which is cosecant squared x. Okay, so from there, I'm going to need to move, well, oh, and I messed up on that one too. Sorry. Derivative of anything with a c is negative, so cosecant squared x would actually be a negative, right? Because if I take the derivative of cotangent, I'm going to end up with negative cosecant squared x. Okay, so I'm going to move to the back side of my paper and simplify this. So let's see, I'm going to have negative cosecant x cotan x minus cosecant squared x all over cosecant x plus cotan x. All right, now simplifying that, I'm going to pull out what they have in common. They seem to have a negative cosecant x, leaving me with cotan x plus cosecant x all over cosecant x plus cotan x. And we can see that these reduce, and I'm just left with negative cosecant x. Now the problem is that's not what I was originally taking the integral of. I was originally taking the integral of a positive cosecant x, right? So that means that when I'm all done here, if I ended up with a negative cosecant x, I need to account for that negative by basically making what I took the derivative of to be negative, right? Because if I had taken the derivative of this being negative, right, that negative would have stayed throughout. Which means that when I factored out this negative, it would have become positive, and I would have had positive cosecant x. Okay, so, when we're taking the integral, where are we? When we're taking the integral of cosecant x, we're asking ourselves, what did I take the derivative of to get cosecant x? And in fact, you would have taken the derivative of a negative ln of the absolute value of cosecant x plus cotan x plus c. Okay, so I know that that's quite confusing, and nobody's asking you to derive those each time, but you would definitely want to memorize these integrals. Other than that, there's not much else new on this piece of paper that I gave you. I kind of just printed out all the tables that they had in 6.6. I felt like it was a really good review, so I would definitely go back through all this. The only other new thing on here is on the back. And it's how do you take the derivative of a base b, right? So we've only really done the derivative of ln, okay? And so this is saying, hey, how do you actually take the derivative of a base b function? I'm sorry, a log base b function, not just base b, log base b function.